So today we're dealing with Chapter 6 on exterior finishes. You know, the stages of construction, if you look down on this bottom of this title page, I've got Chapter 2 where we spent time dealing with the excavations and foundation of a building. And then Chapter 5, we were dealing with framing and sheathing of a house. Chapter 6, we're dealing with exterior finish, and that's not just the paint colors. Who cares about paint colors? Well, some people do, and I guess it's important. But it's about the outer shell of the building. Once we have a frame, we have to clad it with something. So we clad it with siding, with brick, with shingles, as they've got in here. On the roof, that's part of the cladding. So all the exterior surfaces is really the cladding of the building. And including the windows and the doors. And so the goal is to get the building to lock up so that the nosy neighbors can't walk through when you're gone at the end of the day when you're building this thing without breaking and entering. So you start securing, and once you can close it up, you can put things in there to secure them, but you can also start working on the interior too. So that's what exterior finish is about. So let's start looking at those categories. Basically going to start dealing with protection from the weather. That's what the outdoor cladding does, is it seals up the building, gives you a building envelope, as we would say. And so the roofing is part of that. The windows and doors are part of that. The siding, any of the other exterior sidings, or like brick or stone, and exterior trim and finish on the outside of the building also. Protection from the weather, well, the first thing you want to do as soon as you can is get some roofing underlayment up on the roof and some drip edge. Then you're ready for the roofing. Ideally, if you could put the roof on as soon as possible, that's better, but sometimes you have to wait for that. But, a good roofing underlayment job can allow you to keep everything dry at that point, because until then, every rainstorm you get gets all the studs and framing wet, that you're trying to keep it at least below 15% moisture content, and every time it rains, it gets wet again, and then it can start twisting and all that. But anyways, the structure is considered closed or made weathertight once you have this outer cladding of all these components, the windows and doors, the house wrap, the siding of whatever it is, the roofing materials, whatever kind, including the underlayment. So when you're looking at this picture here, you can kind of see it, that you have to install the bottom roll of roofing underlayment first, and then the next one laps over top of it, and the next one laps over top of it. So you really install them just like shingles from the bottom up. The other thing is you see the drip edge, and it's an important detail to notice that the bottom of the roof, we only see a little corner of it here, but the bottom of the roof, that roofing underlayment can't be lapping over top. It has to be underneath the roofing underlayment. So you have to install the drip edge first, and then install the roofing underlayment so it laps over top of that. Now on the side of a gable like this, on the gable roof, on that slope, you can have the drip edge on top. It doesn't matter. But you basically have to think about the journey that a drop will make. And that tells you kind of what has to go on top of what, because you don't want, if you have the drip edge on the bottom lapped over top of the roofing underlayment, then the water can roll right underneath that and inside the cornice and start rotting things out and making stains on the soffit plywood and that sort of thing. So roofing underlayment in modern times, it gets a little fancier. This stuff that I had back on this page was roofing felt paper, the cheapest form of roofing underlayment. They come in two different weights. One's called a 15-pound weight, and the other is a 30-pound weight that's twice as thick. But it's still paper, and it tears pretty easily. It's an asphalt embedded paper into the paper. Roofing underlayment comes in plastic forms and other elaborate synthetic underlayment. So the synthetic underlayment is much more durable and will last longer, easier to put down in that, first of all, it has instructions on there where to nail, so how to lap it and those kinds of things. But in the problem with roofing underlayment, the building felt traditional roofing underlayment, is that wind can tear it up in the middle of the storm, and next thing you know, it's not keeping any water out. It's basically a roofing material of sorts, but it's supposed to be your underwear for the roof, kind of a to seal up the building. The house wrap is meant to be an air barrier as well as a moisture barrier. So again, you install the first layer at the bottom, and you need it to lap over top of the drip edge by a little bit. And then you need to have it come up over top of the peak of the roof as you lap one on top of the other as you go up. And then house wrap, we call this weather barrier called house wrap. This does the same thing on the wall to a certain degree. It's supposed to keep, moisture out, vapor out. It's considered a vapor retarder, so that's why I have the red asterisk on this page listing that. But it's also an air barrier. If you look at Tyvek or any of these house wraps, these synthetic house wraps, up close you'll find that it's a woven material, not that much different from the blue tarps. It's more sophisticated than that. It's meant to be allow moisture to diffuse out that evaporates. So if you get a little bit of moisture in the wall, it can diffuse out rather than just stew in the wall. But it is supposed to also lock up to keep air from blowing through the wall. House wrap, sometimes in old houses, you'll find when you do some renovation, you'll see that they often used cardboard, rolls of cardboard as the house wrap. Or sometimes the roofing felt, the paper roofing felt. The problem with that is that the roofing felt was too good of a barrier. You need the house to breathe so that any moisture that gets in a wall can evaporate out. Here's an example. Okay, I forgot I had that picture up here. This picture at the top is showing you roofing felt being used as a house wrap. It's not an ideal situation. It's okay in a dry climate to do this if you got a low humidity environment, but in Louisiana, it's a horrible idea. We have all kinds of problem with moisture invading our wall systems. And when you seal it up tight this way, it sounds like a good idea, but if you seal it up tight on both sides, any flaws in that system, the moisture collects and it just stays there and rots and stews and molds and everything else. Doesn't dry out ever. So you see the highlighted second bullet here. Synthetic house wraps contribute to reduced air infiltration, reduced drafts, reduce leakage through the walls. And that's a very important thing. And you see this bottom picture on this page, another no-name brand of Tyvek. It's called Typar. You think it kind of seems a little bit like they're mimicking the name of Tyvek, a little bit. So like the roofing underlayment, these house wrap materials should be installed from the bottom up in a shingled fashion. So when you have a big roll, and some of these rolls of house wrap can be 8-foot long rolls easily, and you basically roll that around the house, and it does have a top and bottom, so you really shouldn't be putting it on upside down, or most of the designs do. But you lap it around in a way where you start at the bottom, and then if you're going to have to put some up top to lap over top of it, it needs to be overlapping it. The other thing you see around this window on this page is some tape, some special sealing tape that's meant to go around windows to seal against the house wrap. I don't see it in this other picture here, but let me back up to the picture here on this page. Maybe I'm seeing some of it. No, I don't know exactly. I think at the bottom. Well, the bottom is more important, so let me show you a picture of that. So first of all, think about the building envelope. I mentioned that term earlier here, but you know that you tend to have air leak into the building. In a wintertime model, the air is leaking in because there's air that's leaking out. And so for every inward draft that you detect, there will be an equivalent outward draft where the air is leaking out of the building. So some people would argue, oh, well, but hot air rises and it expands, and so then it's more air leaking. But, you know, the amount of actual air going into the house on the whole is still, the intake and the outtake have to be equivalent. So what happens when you have a leak in your attic or your ceiling deck, the air wants to leak out of there. That creates a suction, which causes the air to be sucked out through the cold draft. So that in the wintertime, you have cold drafts coming in to your hot air, your conditioned air in your house, and then the hot air is leaking out. And so if the air is not hanging around long enough, it doesn't matter how well insulated your walls are, so that you have to have a well-sealed system, or else what's the point of insulating? Now this picture is not really showing insulation in the walls. They're just looking at the air leakage. But around whether you have windows leaking or doors underneath or around doors leaking air in, or sometimes at electrical outlets on walls, when you have an electrical outlet on the outside wall and one on the inside wall nearby, the air will leak through one and through the other into the house. I've heard noises in houses up in Canada where in the very cold weather this dynamic gets extreme, of the cold air being sucked in to the point where I could hear the sucking noise. I mean, it was just a whir. So, oh my goodness, we've got some holes to seal. And here's the thing, when you already have the house built, this is not so easy to seal up all those holes. When you're building the house from scratch, it's really not that much extra effort to do it right and seal all of these areas where air will leak in and leak out, if you do it right to begin with. But getting into the attic and climbing around and sealing holes around chimneys, around attic hatches, around recessed lights, bathroom vents, all kinds of areas where we lose air. And then, of course, air coming into the building. If you've got a door threshold that's not fitting well, the door seals aren't working well, the door wasn't installed very, very well, so air can leak through. Same thing with windows. There's a window unit itself, and then there's how the window unit is installed. So we'll see some examples of that coming up too. So it's like a hot air balloon. As air, you got to heat up the house, and then it's leaking out, and you got to keep heating up the house, you know, kind of like they do when they're heating up a balloon to let it fly. So it shows here in this graph on this page kind of the percentage of air leakage and how much there's importance to this. But the biggest area for leakage of air that matters the most, and the most important area for insulation, is on the ceiling deck. So that's the most important area, because if you can stop it from leaking out, it tends to reduce the amount of sucking of air, cold air in. Now, when we're talking about the summertime model, it's still, hot air still rises, and that's still going on. But the air leakage issue is a little bit different kind of dynamic, but it's still the same principles here. Hot air rises, and it's still coming up into the attic because the attics are typically hotter. But anyways, so there's three ways that heat is lost through a building. You'll see this chart. I'll show it in a couple of chapters here. But radiation is the first one. See, and we're not talking about radioactive material per se, not that, but the radiation of the radiating of the sun. The sunbeam. You know, when you stand in the beam of the sun, even through a window, or you can feel the heat of the sun, right? If you're standing in front of a campfire, the glow of that heat doesn't have to be a lot of light, but there's heat even from hot coals, and you can feel that radiating. And if somebody stands right in front of you, you can't feel it. If you get into the shade, the temperature is very different than it is in the sun. So the sun shining through the window is a really good example of how radiation of heat from outside in the sun can come through. And so we use reflective coatings on windows to reflect some of that heat away here in the summertime. You know, in the wintertime, we actually want the reflective coating going the other way to take the heat that's in the building to reflect it back into the building instead. So sometimes they have both reflective coatings going both ways. Sometimes so it depends what zone you live in. In Louisiana, the big issue is not wintertime, it's summertime. The heat is persistent. Vast majority of the year in Louisiana, we run our air conditioners. Okay, step 2, or type 2 of heat loss through a building, conduction. So heat can conduct through materials and between materials. So we call that thermal bridging, as opposed to thermal break. And so I guess I've lost that part of that sentence here, but thermal bridge is the opposite of a thermal break. So we'll come back to that terminology here. But thermal bridge, if you think about, if you were to heat up with some kind of well, think about the pot you put on the stove and how temperature migrates through that pot. And if you've got let's say a cast iron frying pan, it starts off heating the bottom, and eventually it migrates and conducts through to the handle. And now, next thing you know, the handle's too hot to hang on to. The temperature migrates through the material or between the materials. And I mentioned recently in another video how if we go build a wall where we just, instead of filling it with insulation, we just put a whole bunch of 2x4s side by side all the way across in that wall and just have a solid wood wall. Well, wood is an insulator, but it's just not as good an insulator as the insulation we put in the walls. So the R value of a solid wood wall, 3.5 inches thick, like a 2x4 framed wall, but just 2x4 stacked against 2x4 all the way across, you get an R value of 4. Now, the higher the number for the resistance factor, this R value, is the higher the number, the better as far as insulation goes. We normally, in a 2x4 frame wall with fiberglass batting, we can get to about an R11 or R13. And so if you've got a 2x4 or a log cabin wall, you're not going to get the same R value. Well, the thing about a log cabin is it's going to be a lot thicker than 3.5 inches thick. And so that's how they get to an R value that's reasonable. Not ideal. They're still pretty cold buildings, but somewhat reasonable. So if too many framing members in your wall, you start causing conduction through that wall. And so you can have cold spots. And I've been in climates up in Canada. I spent some time in the prairies up in northern Canada, Saskatoon, Saskatchewan, where we were dealing with with 60 below, 50 below temperatures. And you start to have such cold walls at spots that you start to actually have frost building up on the inside of the walls, which is going to cause stains and mold and all kinds of things. So it can get worse as you go to more extreme cold temperatures. But it's still the same process in reverse when we're talking about the summertime model of temperature migrating, heat migrating through that wall into your house, which causes you have to air condition the house more. Whereas in the wintertime, the temperature is migrating through the wall outside and you're losing the heat and you have to heat up the house. So conduction. So one basic thing is how we frame up the house. We reduce the amount of conduction by using as few framing members as possible. Because the wall is already much stronger than it needs to be. That's typically not the issue. It's to find a way to frame up the shapes you need without using so much wood. And then the third way is convection. So you see down here at the bottom, heat transported via air or liquid movement. Okay, if you got a coffee cup full of coffee, which reminds me, let me take a sip of my coffee. Oh yeah, it always helps. Okay, so that heat, if you have an open cup of coffee, is cooling off at the surface. The mug could be insulated, but the top surface is open. Or some of the cheap coffee mugs, they don't really insulate at the top at all, or hardly at all. And so as the coffee, the hot stuff, it goes to the surface, hot liquid rises, just like hot air rises, comes to the surface where it's being cooled off, and then those molecules, as they cool off, they drop down, and so you get this current that goes on in the coffee cup that you don't even know about. Very kind of a gentle current. And as it's convecting, there's convection going on, movement. We end up with the liquid moving around. Well, that happens in the air too. So if you had a framed up wall and you said, oh, the inspector's not going to know this, I'm going to close up this wall right quick, and we don't even need to, we can save time and money and not bother to put any insulation in the wall. And who's going to know? Well, then you end up with a wall that's just a cavity of air. So if you've got a cavity of air in there, it has an R value of sorts because there's air in there. And if it's sealed up pretty well so it's not leaking, well, then that helps. But what's the deal here? Well, the air molecules can then in the wintertime, float over to the outside wall where it's cold and cool off. And then there'll be convection. It'll move around the current just like the coffee cup liquid does. And so that you end up with air floating over, that's cold now, floating over to the warm wall and cooling it off. And so your wall will get cold a lot more easily when you got freely moving air inside a wall. And so that's one of the reasons we use fiberglass batting in a wall. We'll take this woven blanket of fiberglass batting, we put it in the wall, and it needs to stay light and fluffy so that it's holding the air molecules put so they can't move around. And the fact that they can't move around, they can't convect. There's no convection. You're stopping that process. And the air molecules, if they can't move around, are a pretty good form of insulation then. Even better than that, it would be foam. When you have foam insulation, you've got, well, not even just air, it's some other gases in the foam, but that's creating cells that don't move at all. And so it's even a better form of insulation. So foam insulation of various kinds, spray foam and solid foam sheets, are much better than fiberglass batting. The R value per inch is better in foam insulation than it is with fiberglass batting. Oh, and the other thing about fiberglass batting is that it's only good, it's glass. So if you've ever taken a Pyrex or glass or coffee mug out of the microwave after heating up something and it's hot, it conducts very well. So it's not a good insulator. Glass is a good electrical insulator. It's a poor thermal insulator. So that's what we're talking about, is thermal. We're talking about heat. So fiberglass is not great by itself. And so if you jam it into a crack, you're pushing the air out of the blanket, out of the fluffed up fiberglass batting. It's not a good insulator at all. So you never cram fiberglass into cavities. You don't want to compact it. You need it to be light and fluffy. Okay, so that's more about insulation than we need. We'll really talk about insulation in more detail in Chapter 7, but we kind of need to talk about both sides in order to talk about heat, because these things are combated in different ways here. So convection is mostly combated by insulation. The conduction is, we combat that by sealing the building up so it doesn't leak, and by using just the number of framing members, all kinds of special advanced framing techniques to reduce the amount of framing members in the wall and the ceiling and such. So, talking about sealing up the attic. In Louisiana, many of us have these attic stairways like you're seeing here on the right-hand picture. In my attic, well, I've gotten rid of a lot of those boxes, thank goodness, and I got a new furnace since then, but otherwise, this little invention that I put up here is still working very wonderfully. It's a door. It's an exterior door that I mounted horizontally over top of the stairway, and I had to frame it so that it's up above the stairs a little bit, because the folded up attic stairs take up some space in the attic, and so, but when it's closed down, it seals up that attic, because that attic stairway is never well sealed and never well insulated either. And so this gave me an insulation in that door and a sealed up door threshold on all sides. I got rid of the bottom of the door is right here, and I actually got rid of the threshold and put in another piece of door jamb material and frame here. But anyways, that has helped save a lot of energy for me over the years. Oh, and then since that's this picture, I glued a bunch of foam sheets on top of this door so that it's even more insulated than this. Now, looking here, what you're looking at on the left-hand picture is a recessed light fixture. So normally with recessed light fixtures, you have to keep the insulation away from most of them because they're not sealed units. What I did is I replaced all the recessed lights in our house when I moved in to a sealed unit, which is a little more expensive, but mostly, when they talk about contractor grade, sometimes that means good and cheap. And so the boxes of contractor grade recessed lights typically are often these a non-sealed unit. And so by doing this, first thing is we call those sealed units, we call them IC. Well, we don't say IC, we say IC for insulation contact recessed lights, that you're allowed to have the insulation touch the unit because it's got multiple layers of walls that are sealed so that the temperature doesn't migrate through very easily. You've got sealed air spaces between so that it helps to thermally isolate, create a thermal break between the materials. So you're allowed to have the insulation contact. The other thing I did was I went across, by doing that, I sealed every leak in the ceiling deck, and it took me 3 weeks going around, sliding around in this insulation, getting that itchy fiberglass insulation where the sun don't shine. It wasn't a pleasant sight or comfort. But every electrical wire that was going into, I didn't want to fill with caulking because I might have to push a wire through there, but I stuck preformed foam. You can buy it, it's called caulk saver, and I can pull for caulking, and you can pull the pieces out and shove them in the hole. And so I was just kind of showing you, usually it wouldn't be sticking up like that. I would pour off a piece. I was just trying to show what it looks like by sticking some in the hole around the wire to seal it up. But all of this helps to reduce the leaks into the attic from the main house in various ways. Every electrical light fixture in the ceiling deck needed to be sealed up through a series of either metal HVAC tape or fireproof caulking. And around the fireplace and around anything that could possibly air leak. And so we basically had to think about that through the whole attic first. And because I was getting ready to blow a whole bunch more insulation in this attic, because this insulation settles, the fiberglass blown or the newsprint cellulose insulation, it all settles over time, so you need to re-blow some more in there every now and then to keep some light and fluffy stuff in there. Okay, so in modern building codes, to get your final occupancy permit, you have to pass a blower door test. Well, they don't have a fancier name for that, but you're basically depressurizing the house. You see what this red grainy picture is showing you is they put a temporary door in there, and I'm going to show you a picture of it right here. Here's one with a fan on it, and it blows the air out of the house. So back it up again so that the air is actually being blown outdoors, and that reduces it lowers the pressure inside the house, and you can measure that pressure. And that can tell you how many leaks you have in the house, because per square foot, per cubic feet of the building, you can figure out what is an acceptable level of leakage and what isn't. And it affects everything, because if you've got air conditioning and heating ductwork in your attic and it's leaky, then it could be sucking air from those too. So that's an important thing. So you can actually do a test separately on your ductwork to see if it needs to be sealed up. On an older home, it could very well have a bunch of leaks in it, which means you're sending air-conditioned air or heated air out in the neighborhood as it goes up into the attic. Okay, so anyways, the blower door test. You're you're measuring the negative air pressure. Okay, so in doing so, there's a bunch of tricks you can do. I could go on and on, I guess, about this, but it started in the building codes in 2012, and it's been there ever since. It's just that it's getting more accepted, so that even here in Baton Rouge, they do these tests now. Now, if you've ever seen somebody promote and want to do an energy audit on your home, sometimes third-party companies, they often will do it for free if you are going to, with the idea that they can get you talked into getting some energy retrofits, like sealing up stuff, more insulation, better windows, whatever, that they can sell you. And it's not bad. I mean, they can improve it, but they start off by testing it before and afterwards. That way they can prove that how much of a difference they made before and afterwards when they do all the improvements. But you see the outgoing air, the inward leaking air, the outward leaking air and stuff in the different colors. It's going to suck air in from certain places. And so when you're looking for the inward leaks, you can take a smoke machine around the outside of the house and have somebody else inside looking for the smoke, which is really kind of an oil, that they cook, is what the smoke machines really are. But it's a way they like to do it in a way where most of the smoke is on the outside, so you don't have this oily, smoky area inside the house. And you're just getting a little bit of smoke, and you see, there's something over here we need to seal up, and that sort of thing. Okay, roofing, my goodness, those are some long socks on that guy. So in roofing, we're talking, there's things that are involved with the roof here, and we're looking at the finishing of the eaves and the rakes of the roof. So I had to tell you what the rake of the roof is. The roof drainage, the overhangs, the rain protection, the ventilation of the roof, of the attics. So ventilated roofs compared to unventilated roofs, and then the shingles themselves. Let me just go through this lightly at this point here, but important. Here, they've got some kind of scaffolding so they can work from the bottom, and generally, once you have to install shingles or tiles or whatever kind of roofing material from the bottom up. But anyways, we'll get back to these guys later. But here's a picture we ended off with, in chapter 5. And so when you're at this stage, you're ready for dealing with the roof. And so they've got the fascia board on, or at least basically on there. It looks like it still needs a little bit of trimming and stuff. But it's there so that you can put your drip edge on, and define where the drip edge goes, at least. And so the eaves and the rakes are finished with the fascia before roofing is installed. And so when we're talking about the rakes of the roof, that's going up the roof along the rake board, the rake fascia board, which is going up the gable. So you see on this house, looks like it's all gable roof everywhere. And so all of those areas on the gable end here where you can see the triangles. But you need fascia all the way around. But I mean, let's just take another page here to kind of describe a few of these terms. So you'll need to know these terms. And I have some better pictures, I think, in the study guide that will show this. Maybe I keep meaning to put them here. This came from the original textbook. Look at these bullets here. Drip edge, rake board, fascia. See how that's spelt? Fascia. F-A-S-C-I-A. Fascia. Fascia. We often pronounce it as. And soffit. S-O-F-F-I-T. Soffit. So they're weirdly spelled words that you need to get to know and be comfortable with. The ventilation strip, or a ventilation of some sort. We'll look at the different kinds of ventilating. And then rain gutters are showing too in this picture. So rain gutters get attached to fascia board, but the fascia board is that finished trim that we were just looking back at on this page. All that white stuff, this is all fascia board. Probably 1x6. Yeah, I'm certain it's 1x6 material. A high grade 1x6 finished material meant for this purpose. But anyway, so you can kind of see it in the picture where, let me get down to the words where it says wood fascia. And there it runs up here. Oops, I clicked on the words, so I had to come back. Got to be careful in a PowerPoint. But anyways, now this horizontal board up underneath the cornice, underneath the overhang, if I can put it that way, we call that the soffit, or the plywood soffit, or the soffit plywood. And it's typically in there when we have a roof that's designed in that fashion, where we'll put either a continuous ventilation strip or we'll cut out rectangles for some aluminum screens with netting, mosquito netting in them to keep the bugs out, so that you can have ventilation periodically, at least every 8 feet, with these rectangular vents, or else a continuous strip all the way around, which is actually better. More continuous is always better, because this is the intake ventilation. This is where the air goes in the attic, because you need an air change in the attic in order to ventilate the moisture out and the heat. So the drip edge is right up against the roof. You can see the metal drip edge in this picture. And then the rake board is going along the gable, basically. So better off to show a better picture, but it's what else I want to show you. The soffit plywood I mentioned is up underneath. Same in each one of these pictures, they've got soffit plywood. In this middle picture, it doesn't have fascia board. See that? It's trimmed kind of funny. That's not usually preferred, let's put it that way. Less expensive houses, they might do it that way. Okay, so that's a couple of things. You definitely need to be able to recognize fascia board and soffit plywood, or the soffit board, whatever it's made of, and know where the drip edge is. Well, that's just underneath. You can see metal drip edge on the upper picture here. It shows up. Oh, they got a wooden drip edge in the middle picture. The bottom looks like they've got an aluminum drip edge and aluminum fascia covering the board. So that's another technique. So looking at those parts, because you'll have to recognize them on a test, but when you look in the study guide in the area for Chapter 6, you'll see I have a different picture in there that identifies them, and that's the picture you'll see on a test, so it's worth paying attention there. So ventilated roofs need to keep the roof cool, and they also need to move moisture that collects in their attic and ventilate it back out through the outtake vents. So you have intake venting and outtake venting, and in general, the air goes in at the soffit and it goes up out in a vent that's up near the top or at the top of the roof. So when you have heated air that's heated in the, that's air that's warm and in the attic is sealed up and it's not properly vented, yeah, you're going to store more heat up there. So when you have air inside an attic and it's not all filled up with insulation, well, then it probably should be a ventilated roof. So what happens is that then you have this hotter air in the attic that can hold more moisture, so it does, and since the moisture that leaks into the attic then collects, and then you can have that condense in the winter time, because the hot air will condense and it'll heat up the snow on the roof if you had snow and cause ice dams. So that's a problem that happens from having a roof that's not properly ventilated enough. You need airflow, because the air that goes in at the cornice and goes up into the attic will help push the cold air, the warm, moist air out of the attic in the wintertime and keep you from having mold and rot. That's where most of the mold and rot happens in an attic space, is from the wintertime action. In the summer, everything is so hot that you can hold a lot of moisture inside the air, fully evaporated, and it's just less of a problem. How does mold form, for instance, when it's so hot up there? But anyways, so there's baffles that we put in to keep right at the edge of the wall and the roof where they meet. It's a tight area for ventilating. And so we often have to install a spacer to keep the insulation from clogging that area up, so that air can still flow past the insulation into the attic through the vent that's on the cornice, on that overhang. So anyways, the statement you see here, I've got it on several pages. Roof ventilation under the sheathing and above the insulation helps to remove moisture that enters from above or condensation from below, and reduces the risk of ice damming in cold climates. So it causes less ice damming because of that. What happens is that on the roof, if you got warm spots on that roof, the snow will melt, and as it comes down to the overhang where it's cooler, where there is no ventilation, it refreezes, and it refreezes up underneath the shingle layers and can tear up the shingles as the ice expands. So when you've got a bunch of icicles on your roof, you have failed with your ventilation. So this is the picture kind of showing you that in the top picture, it's blocking the airflow, and so the air in the attic is above freezing enough to cause the snow to melt on the roof. And then it comes down to the edge of the roof and refreezes as icicles and ice damming. Whereas when you have proper ventilation, then the air in the attic is colder and you don't have this ice dam problem. You also, with the airflow, you're getting rid of the moisture, so you're causing the air to be drier in the attic. So that's a failure. When you see icicles like this, that's a problem. Now, when you see icicles like this on a tall building, you should stay away from that building, because on high rises, when icicles form and they drop, they kill people. It's like they come down and they splay you open like a big spear. So they're very dangerous. But here, they cause damage to the roof and to the fascia, but a lot of it's to the roof. So it's a big issue. So this is caused by improper ventilation of your attic space. So this is back to my attic with the dirty old fiberglass insulation. I put these paper strips up that tell me when I get up to that R60 mark on that paper, then I have buried the insulation enough to get to R60, which is way higher than we need to get in this region. But you see those gray, silvery gray things that are over there at the edge of the roof, where the edge of the bottom of the roof kind of meets the wall here. Those are called baffles. So I've got it written on this side panel here on this page. It says roof ventilation baffles should be installed anywhere that the attic insulation could block airflow. And I was getting ready to fill it up with a lot of fluff here. And so these things are about 4 feet long. And so I carved them enough to stick them down to into the cornice enough to kind of be confident that they weren't going to be blocked from airflow. So that way I can fill up against those baffles with fiberglass insulation blown in there, or the cellulose if I was to choose that, and not be in danger of blocking the air passage into the attic for the intake air. So this is what it looked like afterwards, and you can kind of see over on the right-hand corner, you can see one of those gray baffles kind of peeking out through the insulation. So I could fill her up, blow her in with, and as long as I didn't bury those things, I could count on getting good amount of having proper airflow to not cause a problem there. So again, the roof ventilation baffle should be installed anywhere that the attic insulation could block the airflow. So for me, it meant going around to about 200 places or something and doing that on my house. This area that doesn't have insulation is an area that's actually not part of the house, so it can remain uninsulated, and it gave me a place to store stuff over a patio. Here we are. There's that patio again, and you can see how I kind of blew the insulation wherever I needed to here. Anyways, look at this roof here. There's frost on the roof. You say, oh, that's good. Well, the fact that the frost is only at the overhang is an indicator that you don't have a properly ventilated roof, because it's only cold at the edge. And so this isn't going to be a problem in this environment here for ice dams, because it's barely some frost. But you can look at the patterns of frost or snow or other frozen material on a roof whenever you have it, and diagnose some of the issues. If it's nicely even across, then, well, that tells you something. When you see how it's only frozen at the edges, that tells you you don't have proper ventilation. Okay, we're back to the guys with the long socks. Well, not this guy, but the barebacks and the whatever, framing up the houses the way OSHA would freak out. But they are installing some soffit plywood or soffit boards and ventilation strips underneath here. So this is kind of what that can look like in here as a ventilation. This is the best ventilation you can have for the intake venting, because the corners of the soffit plywood are often where it rots. And it's not, people tend to attribute that to a leaky roof, but it's really the most leak-proof area of the roof, because you got all those shingle caps from the hip roof in this corner there, so that can't be it. And so really it comes from improper venting. So that's where the moisture doesn't get to ventilate. So a continuous venting like this actually gives you better venting. Okay, the soffit vents, which are really the intake vents where the air goes into the attic, they work together with the ridge vents, the gable vents, or the roof surface vents, which are the outtake vents, to remove warm and moist air from the building and to keep the roof cool. So I've been saying this several different ways, but here it's in writing, and this is kind of an important thing. You know it'll show up as a test question in some way, shape, or form. So the venting helps to keep the roof cool in the winter, in the summer. Actually, you'd be surprised, it keeps it cool in the winter often too, but it also keeps the humidity down, and the moisture allows it to evaporate out of the attic wherever it condenses. So here's a gable vent up high, so that's why it's an outtake vent, because it's up higher. Some of them are up so high that they're triangular, so they're right at the peak. But also, besides gable vents, you can have ridge vents that are right at the top of the ridge, where you take a sock and cut out a section at the peak, and then they cap it up and cover it with a contraption like this, so that, and maybe like this case, meant to have shingles on it so it kind of hides. And there's other ones there's a lot of different types of ridge vents, but they're at the peak of the ridge. The problem we run into in Louisiana with hip roofs is we just don't have enough ridge for this ventilation to add up to very much. And so when you get talked into by a roofing contractor putting ridge vents up and calling that a day, declaring victory with that alone as your only outtake venting, you're going to have a hot roof, and you're going to have decay problems, because you're not going to be able to move enough air out of this roof. So you're supposed to have a square foot of intake or outtake venting for every 150 square feet of roof. So 150 square feet of attic, actually. So that means 1 to 150. So for every square inch of vent, that's supposed to represent 150 square inches, which is just a little bit over a square foot of venting. So the reverse is true if you look at it that way too. So here's some turtle vents, or roof surface vents, maybe a more fancy technical term, but sometimes we call them turtle vents. They're covering. And then there's the spinning whirlybird kind of turbine-looking vents. They're basically roof surface vents of sorts also, but they tend to leak pretty well. So the problem in Louisiana particularly, we get frog strangler rain that comes right through them. So they don't spin fast enough to something you can count on not to leak, except in extreme wind conditions. So I'm not a big fan of the whirlybird type of spinning surface vents, because I've been in attics where they've rained upon me, so I know you get water in your attic that way. So the soffit vents, again, same statement, just written on a different page. Those are the intake vents. The air goes in that way, and then it goes out the top. So the soffit vents, which are the intake vents, work together with the ridge vents, like what you see in this picture, or gable vents or roof surface vents, which are the outtake vents, to remove warm, moist air from the building and to keep the roof cool. So I didn't have enough venting. I didn't really had just the ridge vent in my house, and so when I first bought it, somebody had gotten rid of the other outtake venting, and last time they did the roof, and they had a very hot roof. The temperature in the attic was like 170 degrees in the summertime, which is pretty darn hot. It's getting up there where you wonder whether you might be able to, in some cases, boil some water, up there. It's not good, because the higher the temperature differential between what's in the attic and across the other side of the ceiling deck inside your house, the more heat that's going to migrate through that system, one way or the other. So when I've changed and put proper venting in here, I'm able to get the temperature down to 110 degrees if I want to, or 115 degrees, depending on whether I turn on fans and stuff. Now, we've been talking about the vented roof and all that venting. There is such a thing as an unvented roof. And so this is an example. There's something called SIPs, or they're called structural insulated panels. They're basically OSB on each side of a big block of foam. And you can buy them, and they can build your whole roof out of them. And so that's kind of one system. The other thing is more common nowadays is spray foam, to actually have spray foam sprayed right up and nested into your attic, so that your rafters are actually embedded in the spray foam. But if you do that, then your whole attic space below the insulation is an unconditioned place that you can literally habitate, but you better not be venting an attic once you've done that, or else it's a waste to go and use that insulation up there. So let's look at this picture. This is spray foam, and you can kind of see it's embedded around the rafters. Sometimes it's thick enough you don't even see the top of the rafters, but they're kind of filling it up along the rafters like this. And that's a spray foam, probably a closed cell spray foam. There's also an open cell spray foam that's a little bit less sealed. This stuff can be very well sealed. For sealing up a building. Assemblies with spray foam insulation are more resistant to air leakage than assemblies with conventional batt insulation, so they create a potential for reduced energy consumption for heating and cooling, because you're also getting rid of all the leakage. And if you're keeping that roof cool, that's also helpful for the shingles themselves. So this is a truss roof. I can see those brackets, metal brackets on each side here of some of these connections. So there's a lot more framework than you might see in an attic down here. So now we're looking at the asphalt fiberglass shingles here. These asphalt-based shingles, they're cheap when the oil prices are low, and they get more expensive when the oil prices go up, because the asphalt comes from the oil, the last stuff in the barrel, as we talked about in chapter 2 when we were talking about asphalt paving. Besides asphalt fiberglass shingles, we've got wooden shingles, almost exclusively cedar, either as shakes, which are chunkier, thicker. They've been split with a wedge, whereas shakes are big chunky things split with a wedge, whereas shingles, cedar shingles, are split with a saw, where they're actually nice and smooth with a saw cut, so they can cut them thinner for shingles. So here's some wood shingles that have been sawn. They're more refined and smoother. Again, they have to be installed from the bottom up, and there's quite a bit to it. There's concrete tile roofing, so that's heavier stuff, way heavier than the cedar shingles or the asphalt fiberglass shingles. So if you're going to switch up and start using this for a roofing material, or this with the clay tiles, it's heavier stuff, so you'd have to make sure your roof is strong enough to support that extra weight. By the way, the expansion and contraction of the clay tiles or these concrete tiles can break these tiles up. And so when you're installing them, sometimes they have holes in the concrete or the clay tiles for you to drive a nail, typically a stainless steel nail or some kind of a non-rusting nail. Or nowadays, I suppose they could use screws, but they want to nail it to within nickel thickness of snug. So you don't want it actually snug. They have to be about the thickness of a nickel up above the clay tile, because the clay tile can expand and contract. And if you fasten it down too tight, it'll break just from the heat, and you'll have broken tiles on your roof, which means it'll be leaking. So clay tile roofing. Then there's sheet metal roof. There's other kinds of roofing we'll talk about, like slate roofing, which is stone, slate, thin slabs of rock. It's wonderful stuff. And it's heavy. I wanted to point out that sheet metal is a special kind of material for roofing, because it's not just the roofing material, it's typically the roof deck too, because it's got structure, especially when you've got these standing seams like this in the sheet metal. Okay, we'll come back to that in another time. But windows and doors, there's flashing and stuff around the windows and doors we have to pay attention to. It's critical stuff in how this stuff gets assembled. So when you're looking at this picture here, dealing with windows and doors, there's three pictures on the right. The top one is at the top of the window or the door. And the idea is you've got the framing up top and then you've got the door jamb nestled around it with door molding. You got casing on the outside, and you can call it casing on the inside too, but there's different kinds of casing. You got brick mold casing on the outside of the building here on the left side of that picture at the top, and then above that you've got a drip edge made of metal, a flashing. So you've got a drip edge for that, and it has to be up underneath the siding. And also the house wrap that they're not showing in this picture has to lap over top of that flashing, so that water can come down off the house wrap and dribble out through that drip edge. So over top of a door or a window, you're really supposed to have flashing. Now, it's not so important when you've got a hip roof house in a single story building going around, because if you got a 2-foot overhang, that's giving you all the protection you need for the top of a window that's up there close to the top of that wall, or a door. Or if you got a window or a door that's under a patio covered area, for instance, it's going to be so well covered that the flashing is probably not important, and maybe, I don't know whether a building inspector would give you a hard time, but that's not where it's important. It's really, really important when you've got a 2-story building and your windows and doors that are at the ground floor are exposed to the weather, where the rain can come down and get in there. So in that case, you have to flash the top and the bottom. Well, in any case where the window is exposed to weather, you got to flash the top and the bottom of the window with drip edge, with lapping of membranes and everything else. All has to be thought through. On this picture at the bottom, they're showing a door threshold on a second story of a building, I guess, up off the ground. And so in that case, they've got a metal drip edge underneath that door sill, so that any water that does get trapped in the membrane will be sent back out and drip off that edge, instead of continuing on in any way, shape, or form inside that wall system where it can cause decay. So every window and door is an opportunity for moisture to find its way in the building at the top or the bottom of those units, and that's what the flashing detail is trying to we're showing you here. So these are just slices of the wall to look at a view through the top of the wall at the head or the header. You know, the header is right there, but then we call it the head jamb when you're talking about the door jamb itself at the top. Whereas the next slice in the middle of the page is through a horizontal slice. So you're looking down through the side of the side jamb of the door. So we call that a side jamb, but we can also give it the name of the striker jamb if it's where the striker plates, where the latches connect and go through a striker plate to lock the door. Or you can talk about the hinge jamb on the other side where the door hinge is at. So there's some other terminology that can be used. Some of the door and window terminology talk about head flashing and sill flashing, or sill pan. Tapered shims or shingle wedges that are used to help you hang or install the door. So they're kind of showing you that in a couple of pictures here too. Well, for sure in the middle picture, they're showing a shim that's being used to install the door in place. Exterior casing, well, that's that brick casing they're called. It's more chunky. It's like 2 inches wide and maybe 1.25 inches thick. It's chunky stuff. It's used a lot around defining brick, but it's also used in other places too. And then whereas on the inside of the house, you're going to have a little fancier molding, more of an OG shape like you see here on these pictures. So the interior casing. So casing is a terminology for the molding that goes around doors or windows. And then we talk about the bottom of the window. I was mentioning there's a little bit more of a treatment here. First of all, they've got house flashing on the walls. That's the whiter stuff here. It's a house flashing of some sort. It looks like it's some kind of a membrane, but it's like... Anyways, then they used a peel and stick membrane that they could peel and stick and glue down for the bottom apron to catch water, and it laps in as glue. It's lapped over top onto the house wrap, but it's also going back in past the window. And in this case, because they got a big deep windowsill, do you see how thick this wall is? It's framed up for much more insulation in the wall, so it's a very thick wall. So with that, the window gives you quite a window ledge, and so they had to put this pan in here because you don't want any water on the inside of the house either to be dribbling down and soaking into the wall, because in wintertime in very cold climates, or even here sometimes, you'll find that the windows in the wintertime when it's cold out, good and cold, you will find that there's moisture condensing on the inside of the glass. And that dribbles down and can soak into the wall and start rotting the wall out over time if that continues. Well, we don't have as much trouble in Louisiana because we just don't get that many cold days in a winter. We've had some, but not many. Not often. Not enough for it to be as big a factor as it is here. Anyway, so this tells you what it takes in many environments to frame up a window. As before you install the window unit, you've got to get this flashing in place. So here's another example where they flashed all the way around, and then there's some tape that they haven't installed yet because this has window flanges, so it's installed on top of the house wrap, and then they'll take some special house wrap tape and wrap it all around the perimeter of this window to seal it in. Because if you don't, then the air can get past the window. You can have a really perfectly sealed window unit, but what if the installation is crappy? If nobody spent the time to seal that up, you're still going to have air leaking through that building, and you won't get the benefit of that nicely sealed new window. Because that's the main benefit you get from new windows in a house, is sealed windows. The seals are fresh. You get a house like mine was until I just changed the windows out a couple of years ago. It was pretty leaky around those old single pane aluminum windows. Yes, I got double pane windows, but that's not the big factor. It's the sealed part, having freshly sealed windows that are all sealed up nicely. That's what matters. Okay, here's a couple of windows here that are installed together, kind of as a combination unit. They're still somewhat separate with that wood frame between. A lot of windows that would be joined like this would be just joined and screwed to each other so that they would work together as one. But it just depends. They still have an awful lot of extra framing in here. They seem like they made a mistake, and they still had to add another trimmer board in there, to another 1.5 inches on each side, so they got more wood than they should have here. It's not ideal. And a bunch of wood underneath too, so they really didn't know their dimensions well here when they framed this opening to begin with. Here we're dealing with the siding now, the outdoor cladding of the building. Yeah, there's looking at the windows, but there's also that siding that you see down there at the bottom of the picture. House wrap, they actually, before they put this trim up, they put some pieces of house wrap around there first so that it wouldn't be, because they weren't ready to put the rest of it on yet for some reason. And then they'll have to come back and lap everything over top or underneath, that house wrap, so that everything is sealed up on that wall before they finish. And now we're looking at siding. So with siding, there's a lot of different kinds of siding. There's board siding pieces that are like lap boards, horizontal board siding. Sometimes it's vertical board siding, same concept. In a place like Louisiana, the horizontal board siding makes a little more sense. Plywood sidings are 4x8 sheets of a siding-like material that can be installed on the walls, and so it tends to install pretty quickly. There's shingle sidings where you literally take shingles. Well, not too often do we use fiberglass asphalt shingles. We use cedar shingles for sidings, sometimes. It's kind of a bit of a hippie look, so I don't know how, and I don't think it works that well in Louisiana to use shingles, cedar shingles for anything, actually. It's just the humidity and the sun, the combination of that and the heavy rains, it just doesn't do well in the weather. It's wood, so what do you expect? Even though the cedar and redwood and cypress have natural tannins in them that keep the bugs from eating it, the bugs will eventually eat it. Our bugs are tough. And then below that, I've got stucco. So there's the traditional concrete Portland cement based stucco where you've got sand and Portland cement mixed together and going on a metal mesh background. And then there's synthetic stucco. So we'll look at both kinds. And then there's masonry veneer. So that's talking about brick around your house. The vast majority of brick around our houses, almost all of it, is masonry veneer, where it's really not holding up the house. The house is holding up the brick. You'll have brick metal ties laying and bent down into the brick mortar, so that as you lay the brick, it's being held up by the wall, a wooden wall most of the time. Then you can have real stone or artificial stone. Artificial stone will be lighter and will look like stone, but is maybe manufactured pieces, I guess. But still, it's basically a type of stone material of sorts, usually. And then the last one is something really common and popular here in Louisiana for the lesser expensive buildings. It's a fairly inexpensive material, and it's going to require painting and all that, so it's not maintenance free. But that's the fiber cement panel siding or fiber cement board siding, either way. It's basically, the brand name is Hardy Panel and Hardy Board material. So you may see that. If you haven't heard any of those terms before, now that I've mentioned it, you probably will the next time. If you ever go to Home Depot, you can find it in the plywood section where they keep the plywood panels. So, yeah, that's just a picture of siding. Well, let's look at a couple of basic lap boards. So if you talk about the board sidings, when they're horizontal boards like this, they start at the bottom just like shingles, and you work your way up. And you typically are trying to nail it the least amount that you can, because the boards being made of wood, they expand and contract, and you kind of want to keep them put. And whenever you can put a nail into wood where it's going to be covered up or hidden is even better. But that's not always possible with board siding. You've got to lap up. So yeah, there's plain bevel, rabbited bevel. There's a V shiplap. There's a cove shiplap. There's tongue and groove. Now, one thing I want to point out about all this stuff is you got to figure out how to lap it over top. One board has to lap over top so that you're keeping the rain from going in behind it. So we purposely start at the bottom so we can lap them going up so that they overlap and keep the rain from getting in there. But in Louisiana, we have such ferocious rain that it tends to hit the ground. It's been a long time since it's rained lately, but for me anyways. But it bounces off the ground and bounces back up. When I first got here, I go and say, I don't need an umbrella, until I saw what kind of rain we had. And then you go and take this umbrella, a great big golf umbrella, and it still barely keeps your head dry because the water is hitting the ground and bouncing back up and getting you on the pants and the feet and the chest and everywhere else. And then the wind is typically blowing it sideways, so you got to figure out which direction you point your umbrella. Well, it's like a pressure washer of rain. So the house is, the water does get behind this stuff. It just does. Now, the last siding on this page is board and batten siding, they call it. So the idea is the board, this is a slice through a wall vertically. This is the way this is. So the other ones we've had we've had a slice through the wall vertically for these other ones, so we're looking at the side view for all these pictures of siding. But the other one is turned the other way, so we're taking a slice horizontally through the wall, so we're looking down through a cross section of the wall with the last picture on the right, the board and batten siding. So the idea is you've got boards, wide boards, and then you have narrow strips of wood, and that's the batten. So remember Baton Rouge, red stick. So batten, it kind of means stick. And so board and batten. So the idea is that you put the board down and then you put the batten. The reality is that most of the siding that we have that is board and batten is really what we call reverse board and batten siding. And it looks like this. I'm going to go back up a couple of slides, well, one slide to this page. And this is actually a piece of plywood simulating reverse board and batten siding where you got these grooves in there. So then the idea is you put the battens down first if you're making it from scratch like it is in this picture. The opposite of what you have here, you put the strips of wood, the battens down first, and then the boards go between them, and you have these grooves that are the bottom of the groove, or the back of the groove is actually the batten. Okay, that's a mouthful. But anyways, so that's sidings. All you cared about knowing about siding in one fell swoop. And I forgot, I had zoomed in a little closer, but it's the same picture. Okay, so here they're installing some siding. It looks like it could be, they're nailing stuff, so it could be wood siding, but it could even be the hardy board siding. I'm not sure, can't tell. But what you're also seeing in the foreground here is a pump mechanism for scaffolding. So the idea is these boards, you can keep cranking them or pumping them so that you can raise and lower this plank as you go up the wall. And it'd be attached at the fascia board up top somewhere there on the roof or on the soffit plywood or something. So they have corner boards defining these siding boards. So these are 90-degree cuts on these boards. So you cut them just the right length and you install them, and they butt up against these corners. Because the corners tend to take a beating in the weather more. So the corner boards help to kind of define and step that back away. And they certainly make the fit better, because you're not talking about having to miter anything as far as well, nothing gets mitered here. It's all straight cuts. So what else? Let's see. Here's some horizontal board siding on the left-hand side of the page where they've mitered the corner to come to a 45-degree angle together to meet. And so that looks nice and everything, but it also will tend to decay more quickly. Whereas the other boards we were looking at on the previous page, they would look like what this looks like up close. Now, I'm not particularly a fan of how these nails or screws, it looks like, can't quite tell, are sticking out like they are. Now, maybe they glued the stuff on there and then they'll undo the screws and fill the holes. I don't know, but not ideal for them to be proud sticking up like that. So the technique that works best whenever you can afford it or kind of manage to do it is to actually have strips of wood on the wall that the siding goes on so that you have an air cavity behind it where the wood can dry out from behind. And then you have to have a screen down the bottom so the roaches and other critters cannot make their nest in behind there. You don't want to give them a nice little paradise to grow their little kingdoms. So therefore we call those strips of wood furring strips. Furring strips, or furring, is something that refers to a lot of different things in construction. So there's a lot of different things that can be called furring, but generally it's scrap material or a way to cover up stuff in some, you're hiding stuff with strips of wood in some fashion with furring. Okay, so the screening is at the bottom. Okay, so here's another way. You can literally nail this stuff on this woven recycled plastic material as a backing and nail through it, basically. And it is basically keeping it away from the wall enough that you can get some air flow behind it to dry it off, and then the bugs can't really climb through it very well either. So it's a matting, special stuff. Okay, more shiplap or lapping of boards here. And here we've got vinyl siding. The light beige looking stuff is vinyl siding. And then they have real shingles. So they combined a very synthetic material here with a very earthy material with the shingles. So This picture is looking at that 4x8 sheets of exterior grade plywood that's designed to simulate those vertical boards, the reverse batten boards here. And so then when they're made of plywood like this, they tend to have one edge that laps over the other so that you can keep the seam hidden. And then the grooves help you to keep track of where to nail, that you can kind of figure it out without having to actually put marks on the wall for nailing purposes, so that it can tend to work well. And what else here? Then we're coming to stucco. So the Portland cement-based stucco is where we take the same kind of Portland cement we use in concrete, and we mix it with some hydrated lime and some sand, kind of like we would for a masonry mix for mortar. And but we need a lot of it, and we put it down with a toothy trowel. So what you see here on the right-hand side with the real deep grooves in it would be put down with a trowel that has big teeth on it, so they can make sure that you're putting the right amount on the wall, and so you're loading it up. And then, so that's called the first coat, the scratch coat. You can imagine taking your fingernails and scratching through it, but you don't do that. You use a trowel to put it up on there and get that pattern. When it's set up the next day or so, you can come back and put the second coat on there, and that's what you're seeing over on the upper left-hand side behind the words, and that we call the brown coat, and it kind of has a brown look to it if you got a bit of an imagination. And but what you're doing is you're filling the grooves, and the combination of those two passes, the scratch coat and then the brown coat, is you're getting the appropriate thickness of this stucco on the wall, usually on a mesh surface sorts, kind of a extruded metal pattern that was already nailed and chaired up on the wall, so that you could put this on there, so the reinforcing of all that mesh in there helps to give it some strength and keep it from cracking up. So it gives you a concrete-like surface. And then the third coat's not shown here, but a third coat could be a finish coat. And sometimes it's a pattern that you might trowel in there and give it a consistent kind of a swoop. Or it could be a pattern that is kind of meant with some stamping or something, or troweling with a special kind of a trowel that has a pattern or something. So that's cement-based stucco, and we call it that. I usually would call it Portland cement-based stucco, just to be sure you understand what we're talking about. And then the next thing is that we have synthetic stucco. So in modern times, most of the stucco on houses now is synthetically based stucco. So what is that? Okay, well, first of all, they have a system when they combine the synthetic stucco with insulation on a wall. We call it EIFS. Okay, that's a weird thing. EIFS, which stands for Exterior Insulation Finish System. And it's basically putting a bunch of styrofoam or foam sheets on a wall and getting it all nicely installed there. And then it's not a good surface for an exterior surface, but it adds insulation to your value of your house. Increase the R value on your insulation for the wall systems. And then you coat it with this synthetic stucco, and you can make it look like whatever you want it to look like. There's all kinds of things. So this synthetic stucco doesn't set up like in a chemical reaction the way that the Portland cement-based stucco does, and it's not porous like the Portland cement stucco tends to stain, and moisture can get into it and have mold grow into it, so it doesn't work very well. But this synthetic stucco is a very well sealed material because it's basically glorified paint, latex paint, acrylic paint with sand in it and coloring, of course, from the paint. And so you're basically putting this thick, sandy filled paint on the wall and letting it dry like paint dries. And it gives you your coating that you're after, and a very durable coating it is. Very well sealed. So these are on the left-hand side of this page. I've got some names from some of the brand names I've seen. Acrylic stucco can be the name of it, not a brand name, but a type of material. We call it acrylic stucco or synthetic stucco, or plaster finish, sometimes we'll call it, but that's not a very good name for it because we have plasters that are used just like cement-based stuccos. Old houses, inside the house, they have Portland-based stucco, but it's a little smoother, refined material. and it's still concrete based, and it's called plaster. So in old houses, you go to hang a picture on a wall and it won't hang, and your nail ricochets around, won't go into the plasters because it's plaster. But the brand names down here might come to a world for you. You might see that in a store. MX Acrylic, Drivet or Drivet, Sto, S-T-O, Synergy, and Thoro. Those are all brand names for synthetic stucco that are out there that you'll see at places like Home Depot and Lowe's and stuff. So being acrylic based, it's much like mixing latex paint into sand. So that's what I was trying to tell you about in here. Okay, so here's what synthetic stucco can look like. So you can start to look like stonework, because you see those columns around each side of the door that they've got these little blocks in there. Those are pieces of styrofoam that they cut out and glued on here, and then they go coat it, and it starts to look and feel like stonework that you've got in here as detail. That little detail over top of the doors is some pieces of styrofoam that they then coated in synthetic stucco. And sometimes you'll see some fancy houses where they'll buy a fancy leafy looking medallion that ends up getting over top of the door or somewhere in areas that they have a space for it. And they'll coat all that in synthetico, and it looks like synthetic material, and you end up getting what looks like a carved out of stone kind of look, So basically, you pay for this stuff by the square foot, and then by the linear foot for any special details around windows and doors or those columns. You have prices like that. Here's some fiber cement paneling in a commercial project, basically. So there's another kind of cladding of sorts. And then next to that is cast in place concrete, where the holes from the form ties they decided to own it and live with it as kind of the part of the look. Whereas if you didn't like that, you could fill them in with some concrete grout. Here is a mock-up, and I need to show you some better examples of mock-up. This is good. There's nothing wrong with this, but there's some other places where we need to look at mock-ups. But the idea is when you've got an architect involved with your project, they may specify that you need to construct a mock-up of all the different building materials, so they make sure you know how they want them installed, so that there's no confusion. And so it typically means doing a cutaway like this so that you can see the house wrap, and then they've got some other membrane they put on top of that before they put the siding that's installed, and the siding is showing you how they wanted it installed. And then apparently they've got copper gutters, so when this thing is finished, they won't need it anymore. You take it home and finish it and make it into your doghouse, and your doghouse, your dog is going to be pretty ritzy because he's going to have copper gutters. Oh wow, okay. And then this also does show you the proper technique of how we install cedar shingles on a roof. You got to have strapping. You can't have solid plywood up there. You have to have, in general, you have to lap these things. Now, I would expect there should have been another membrane on the bottom section, but I guess I shouldn't critique them too much. Maybe that's, I don't know what to say about that one. But anyways, looks like a doghouse to me. Very fancy one. Exterior trim and finish. We're coming near the end here. Looking at the trim and finish around the building. So if you have decks, well, then and ramps, you've got to make sure that you're using wood that can take the weather. So that generally means at least pressure treated material, but you could use a higher grade material. There's a hardwood material that's got the same kind of natural tannins that cedar and redwood and cypress has. So cedar, redwood, and cypress work well outdoors, but this other stuff is much more refined. It's called Ipe, I-P-E. It's pronounced Ipe, and it's basically a Brazilian hardwood that's got natural tannins in it, and so it's used in ritzy places where they got money to burn. But here's some Ipe right here, so you can see it down the bottom. IPE wood, pronounced Ipe, is a very durable and hard Brazilian hardwood that is resistant to fire and insects. So it's very, very durable. So it's useful in commercial applications too. Around the exterior finish of the building, you got to make sure that the ground is sloping away from the building. It's critical. You will not pass your final inspection if the ground is not, unless you got enough fall from the edge of the foundation down. You need to expose the foundation edge enough that it's not going to soak up and find its way inside the slab, and it needs to be sloping away from the building, especially with the softscapes. We talk about hardscapes, that's like the concrete walkway or the concrete driveway and stuff, or the softscapes would be the garden bed or the grass or the dirt of any kind. And so you need more slope on the softscapes, the dirt and the grass and stuff, than you do on a hardscape where the water is going to hit and roll away more easily. But everything has to be camped up so that there is no wood near the ground. We design these things so that there's no water, no water collecting or getting on wood to stay. So these columns are designed so that there's no wood near the ground. There's some more examples here. Some cladding around the wood to keep some stainless to keep the wood dry with some flashing on these glulam beams. Here's some details around windows that look like overhangs to protect from rain, but their openings fly through. We have some of those around Baton Rouge Community College too. They're meant for the sun instead of the rain, so they don't really help with the rain. They're just artistic, but they do have a little bit of a function about keeping the sun. If the sun is pointing a certain direction, like coming from the south, you might have, or it's the southwest, you might have hot sun beaming in your window in the afternoon. Or if it's in the morning, it could be when the sun is lower in the sky, it's more of a problem. Here's some addition of some Ipe wood around this deck here. So building your decks, you got to make them very durable. And I a little suspect that this would not work well in Louisiana because there should be more room underneath that deck so you can kind of make sure there's no critters living underneath there. That's my theory. Anyways, note this failing foundation right here. It's blowing in here. So again, there's something wrong with that foundation, and it's life-threatening because it could literally cave away and collapse on people inside the building, and they could cause the building to collapse. So there's a serious problem there. But ultimately, the concrete wall wasn't strong enough or wasn't connected properly to that floor system, so that's why it's happening. But now you got to basically dig out, and maybe that's what they've already done, is dig out away from there to take away the dirt that's causing pressure against that wall, because it needs serious repair. So sometimes we have building settlement, and we've talked about that in chapter 2 also. Sometimes the way you can solve it, if your building has settled, if it's settled evenly, so there's still not a building that's falling apart, then you can take the before picture here where they had the water, problems with water flowing in the front door, and just lower the ground everywhere around that door so that the water can flow elsewhere. If you can taper the ground and re-landscape to send that water somewhere else, then you solve the problem without having to deal with the building itself. But there's a lot of techniques for handling water, and I could spend a whole hour talking about that, so I better stay away from that for the moment. Talk about settlement here. Look at this. In Guatemala City, in Guatemala in 2010, in May of 2010, they had a sinkhole of all sinkholes. It's like, my goodness, it's a huge hole. Talk about a pothole, hey? Well, I'm not sure if anybody lost their lives. I never did hear about that, because I remember seeing it in the news and I went back looking for the picture. But certainly they lost some buildings or parts of buildings in here. But just on the next page, you got the details here. This thing is 60 feet across, this hole, and it just happened overnight, And it's 300 feet deep. My goodness. You accidentally drive in here or walk off the edge, it all goes bad real quick. It was caused by a burst storm drain deep underneath the city that washed away natural volcanic pumice that was underneath there. And so it created this cavern that eventually failed here. So they had to go back and fill this and a whole deep cavern back in there and stuff. It's pretty amazing. So just for the fun of it. So anyways, that's enough about chapter 6.